Testing, testing. In the chat, can you verify you can hear this?
Sound? I'm hearing that we have sound. Do we have sound? Matt, do you hear anything?
Yes, I think it's good now, Jordan.
Okay, you guys can hear me now? It's good? Okay, I'm seeing that it's good. I'm just going to try to move through this. We're unfortunately very late here. Don't know what happened. Sorry about the technical difficulties. Just restarted some browsers and all of a sudden it started working. Okay. All right, everybody. Well, anyway, starting again. Sorry for the delays. Welcome to the MIT Bitcoin Hackathon CKB workshop. My name is Jordan Mack. I'm a senior software engineer at the Nervos Foundation. I've been a software engineer for a little over 20 years now. I've been in the blockchain space starting with Bitcoin in 2011, and I've been with the Nervos Foundation since 2020. So on the agenda, first we're going to set our target audience. We're of course we want to provide the best we can to developers participating in the hackathon, but for best results, we really would recommend people that have Bitcoin UTXO experience or Ethereum smart contract experience, at least a little bit of familiarity with that, because there's so much conceptual knowledge here that if you don't have that background, it's going to be pretty tough. Of course, you're welcome to try to move through it with us anyway, but it's going to be a little bit more difficult. Just a little warning for you. Okay, so the first thing we're going to go through is a challenge overview. I'm just going to walk through some of the examples and give a little bit of background on there, what kind of things we were looking for, and what kind of things you can do on Nervos with those. Then I'm going to point out some of the hackathon resources that we put together for developers to utilize, and then we're going to go through a CKB crash course, which is going to help if you're doing something more advanced. This is going to help you get through the system. We don't have much time to do this, so this is going to be very, very abbreviated, kind of like drinking from a fire hose, but we're going to do the best we can. Okay, so challenge overview. The official challenge is just to build something exciting with CKB. That's completely open-ended to you. It's really whatever you want to do. But of course, we want to put together a couple examples just so you understand a little bit more about CKB and what it's good for. So number one, a Bitcoin-related app using CKB's flexible crypto primitives. So what this means is that every blockchain out there uses certain types of crypto primitives. You may have heard of them, like SHA-256, SECP 256K1, SECP 256R1. There's all these different algorithms out there. Every blockchain uses a specific set. CKB is a little bit unique, as then you can actually use any crypto primitive you want, upgrade them as you need them, because it's done at the application layer rather than the blockchain layer, and it makes us more flexible. So we can actually speak the same language as other blockchains, including Bitcoin. So if you wanted to, challenge 1A, example 1A is control assets on CKB using a Bitcoin wallet. So because we have flexible crypto primitives and we can speak the same languages, it means we can actually understand what a Bitcoin wallet is signing and verify that a person, a Bitcoin user with a Bitcoin wallet is a user that can do certain things on CKB too. We can actually authorize transactions on CKB with a Bitcoin wallet. And so this is something that's pretty unique to CKB, and we'll go through a little bit later some of the tools that you can use to actually make that happen. The second idea was to create a Bitcoin SPV-like client on CKB. Now, this one is a little bit more complicated. This is something that if you're familiar with how an SPV wallet works on Bitcoin, you could actually implement that same thing as a smart contract on CKB. And you do this by verifying the block headers, which would be relayed by nodes. And there's not trusted nodes. You'd have anonymous nodes, any node could be able to submit to the smart contract the Bitcoin headers, and then you could actually look at the proof of work that was done, and CKB can understand this, parse the headers, actually verify the proof of work that was done on the Bitcoin chain, and actually make a call on if this is a valid header or invalid header. And so you could do something pretty interesting with that. So anyway, let me reiterate that these are just examples. You're welcome to do whatever you want. The second one was to use WebAuthn to control assets on CKB. So if you're unfamiliar with what WebAuthn is, it's an up-and-coming way that we're going to start using passwords across the entire internet. And it works by using the hardware enclave that's on in your computer, in your tablet, in your phone, which is one of the most secure devices that we have in existence today. And it's usually protected by certain things like the biometrics, like for example, Face ID on Windows or iOS, or the thumbprint scanner. These types of things are actually interacting with the hardware enclave on your device, which keeps your private keys safe. So CKB is, again, a little bit unique in this, is that it's one of the few blockchains that can actually interact with WebAuthn because it requires SCCP 256 R1. So you can actually use a WebAuthn wallet, you can use WebAuthn to authorize transactions on CKB without any dApp wallet at all. So we have a demo for that, which we'll get into in the next slide. And the third idea that we were throwing out there was maybe something with ordinals. Bitcoin ordinals are making a lot of headlines these days, and they've developed a pretty unique system on how they're accomplishing NFT-like functionality. So CKB, of course, we have NFTs out there, but just like anything else, you could extend them. You could use a ordinal types off-chain protocol on CKB. The NFT protocols that we'll talk about in a minute do have an open data area that you can pop whatever data you need into. So you can do something similar to ordinals. Maybe it's something like ordinals stores all the NFT data, the JPEG data, actually in the witness area. CKB also has a witness area. You could do something similar to that. So again, like these are not requirements by any means. These are just some ideas we threw out there to help give you guys ideas of things that you can actually do. And then the judging criteria is going to be the same as on the MIT dev post page. We're basically just following those exact same things to go through the judging. So let's look at some of the resources that we have actually put together. What just happened there? Okay, sorry about that. Sorry. Let me get that back. Okay, resources. Okay, so this is the resource link, and the resources are also on our YouTube video in the description. You can find the links to everything, including this presentation, which has a bunch more links out to other places. So there's a lot of materials out there, and we realize that this is going to be a really short hackathon, and you're not going to have time to go through everything. So we want to give you a little bit of direction on what to look at first. If you're doing something with crypto primitives, we recommend looking at this example, which is the Lumos OmniLock MetaMask demo. So Lumos is a framework that we use. It's a JavaScript-based framework. And OmniLock is an on-screen or an on-chain smart contract that we use to interact with other blockchains. So you don't have to actually build your own from scratch. This one already has the functionality in it for Bitcoin. So what we had described earlier about using a BTC wallet, you can actually do that with OmniLock. And this isn't a MetaMask demo, so you wouldn't want to use MetaMask, but this demo here will at least get you a starting point that you can work with, and you can hack this code apart and actually put in whatever you need to accomplish the BTC wallet functionality. Not sure why it's doing that. That's funny. It keeps clicking out. Okay, next one. WebAuthn. So this is a demo about WebAuthn and how it can control assets on CKB. This demo was actually put together a few years ago, back in 2020 by the Lay2 team, which is one of the builders that has worked with Nervos quite a bit, and really pioneered a lot of the interoperability stuff that we did. So they put this demo together way back in 2020, but back then, in 2020, WebAuthn wasn't supported well enough on very many devices and in many operating systems and browsers, so it really couldn't even be used. It hasn't been until recently that WebAuthn has gotten enough support industry-wide that it could actually be used. So for this hackathon, we thought this would be a really great demo because it's pretty simple, and we decided to resurrect it because it has been 3 years, and in that time, the demo completely stopped working as a lot of infrastructure changed. But we put this together, so it's now fully functional, and you can actually, there's a link in there that you can just click and you can actually see it in action. If you load it on your phone, you can actually use WebAuthn to do a testnet transaction just from right from your phone without having to install anything else. So if you're doing something with NFTs, we really recommend the CODA standard. So CODA is the main emerging NFT standard on Nervos. This one is really cool because it uses something called sparse Merkle trees to effectively compress NFT data on chain. So normally when you have a NFT, there's going to be some type of an identifier that's stored inside the contract or whatever. That is the on-chain representation of this. Now with CODA, it's 32 bytes regardless of how many NFTs you have. So one NFT, it's 32 bytes. You have two, it's still 32 bytes. You have 10,000 NFTs, it's 32 bytes. It's a very concise representation. And this is really important because it's going to enable the storage space required for NFTs on-chain to be much lower. Lower requirements means lower operational costs for everybody in the long term, means higher sustainability, and ultimately it means that you'll be able to mint NFTs and send NFTs for a fraction of a penny, which is really a strong innovation when you consider, like during the bull market when NFTs were really popular, it was costing people sometimes hundreds of dollars to mint an NFT. That's not sustainable. That's not going to be mass adoption, but something like this really is. So we recommend checking this out if you're doing something with NFTs. Now, if you actually want to modify the contract for an NFT, that's a little bit of different story because CODA is very complicated in its implementation. So then if you wanted to modify the contract itself, we would actually recommend a different one. We'd recommend you look at MNFT. So MNFT was a standard that was put out on Nervos several years ago. And this standard was pretty basic in what it did. It's one NFT per cell, which is per UTXO basically, and it takes up a lot more space. It's pretty much the same as like an ERC 721 equivalent, but on a UTXO based chain. So this one's a lot more simple. If you did want to modify something, this is the one you'd probably want to look at. And then if you're going to do something with fungible tokens, then you're going to need our SUDT standard, which stands for a simple user-defined token. This example that I've highlighted here, Lumos SUDT CKB exchange demo, is pretty much the most simple demo that I could find out there on how you can actually just create an SUDT token and move it around a little bit. So this demo will explain it. This is just a JavaScript demo. On Nervos, you don't actually have to deploy the contract to use it because we use a template system. So this is all you need to actually move things around. And let's see. Oh, come on. All right. So, and next, this is the cell model. So if you're doing anything more advanced, then this is where you're going to actually have to get into some more serious developer training. So we have 2 courses that we recommend anybody who wants to actually do real cell model development. And I'm talking, of course, about the on-chain component smart contracts, the 0 to CKB course, and then the layer 1 developer training course. Now, these courses take a long time. Like for most developers that I've talked to who have actually gone through the L1 developer training course, it's taken them between 2 and 4 weeks. Obviously, we don't have that much time for this hackathon. So it'd probably be just bits and pieces here and there. We kind of recommend that if you're specifically doing this for the hackathon, you probably want to come into our Discord and actually ask us some questions about what we can point you to as a resource, because we might be able to point you to the specific piece you need out of the developer training course rather than having to go through the entire thing, or another specific example code here or there, because you're not going to be able to do that in time, obviously. But of course, after the hackathon's over, if you decide to continue with your project, these 2 courses are, of course, recommended. Okay, so next, let's go through the CKB crash course. So I'm going to do this. There's kind of two halves to this. I'm going to first talk briefly, very briefly, at a high level about some of the things that make CKB a good option. And as a developer, you need to know these things on what are CKB's strong points that you can actually utilize and why you would actually want to utilize them. So first, what is Nervos? It's a modular blockchain network built from the ground up to ensure outstanding security, decentralization, flexibility, and interoperability. And what is CKB? CKB is the flexible, interoperable layer 1 blockchain built on RISC-V and secured by proof of work. It's the foundation of the ecosystem. So there's two things I want to point out here. CKB, which is what we're developing on, is the layer 1 blockchain. But there are actually multiple layers. We have a second layer called Godwoken, which is EVM based, just like Ethereum. That's a layer 2 network, so it's actually getting inheriting some of its security and decentralization from layer 1. But we're focusing on CKB, just layer 1 for this hackathon. And so CKB is UTXO based, just like Bitcoin or any of the other UTXO based chains out there. And it has Turing complete smart contracts like Ethereum. So it's kind of like the best of both worlds. So what's special about CKB? So some of the features that it has, it's sustainable limited supply cap, just like Bitcoin. So this one is one of the things that is important to a lot of the investors, is that just like Bitcoin has 21 million, CKB has something similar. It's actually not technically a fixed supply cap, but it is an effectively fixed supply cap for anybody who's a long-term holder. And so the way it works is by depositing in our DAO, which gives you a way to offset inflation 1-to-1, and it's effectively the same type of thing. The tokenomics on this project is pretty deep, and this is one of the things that's most important to me personally when I got interested in the project. So, I mean, we have some resources. If you want to read more about it at a later time, you probably wouldn't have time for this hackathon, but I definitely recommend that. So CKB uses NC Max proof of work consensus. The NC in NC Max stands for Nakamoto consensus. So it's based off of what Bitcoin did with Nakamoto consensus, except it's got some improvements to it. Things like it uses a dynamic block time, which is actually currently about 15 seconds or so, hovering between, I should say, 10 and 15 seconds. And it goes up and down, basically adjusting as needed based on the network conditions. So this is when you're doing something with smart contracts in particular, a 10-minute block time isn't too great. NC Max does what it does is it actually minimizes the amount of time possible that it can do safely without actually sacrificing any decentralization or security. And then it has a RISC-V based virtual machine. Now, if you don't know what RISC-V is, don't worry. I didn't when I first heard about that either. It's actually a computer architecture, just like ARM or Intel-based processors. But this one is a newer one that's emerging, and it's completely open source. And so when you're actually building on Nervos CKB, you're building for a virtual machine that is effectively emulating hardware. So this is not like any kind of a platform or some kind of a specialty environment that they put together just for smart contracts. This is actually the same open standard that's used in computers today. You can actually go and buy computers that are running RISC-V or embedded little devices like that are used in things like remote controls, for example. A lot of these actually are coming out more and more with RISC-V based hardware in them. So you're programming for the same thing. And because of that, we can actually use the same compilers, like Rust compilers, which are much more robust than some of the ones that are being developed specifically for blockchains, because these are being built for a much larger ecosystem for just general development, such as the Rust compiler, which is my personal favorite. It can target RISC-V directly. And so there's no translation, there's no layers or anything. You're actually using real RISC-V binaries. And so CKB is UTXO based on the cell model. So this is, of course, something that's very important for certain things like scalability. We know that the account model used by Ethereum has some issues with being single-threaded, and that's why we look at the UTXO model for the future, because it can run massively parallelizing. And we see that computer processors today, they're getting more and more cores. So being able to take advantage of those cores is actually something that's very important. And it's going to help scale blockchains to actual true mass adoption. And CKB has some really great modern features. Account abstraction is one, which is actually just hitting headlines. You've probably seen it here and there. It's a big, and for a good reason. It's actually a very important one. But this is something that's still, like, for example, emerging in Ethereum. They've got standards that they're pushing out there. It hasn't actually been implemented. Account abstraction has actually been in Nervos since day one on launch, which was back in 2019. And same with state rent. State rent is another important one that we're looking at in the industry. How do you actually keep blockchains sustainable? Because if they're not sustainable, who's going to really build on this? How are we going to have global infrastructure if it's not sustainable and just falls apart in a few years? You need these types of systems. So state rent is extremely important, and it's also been built into Nervos since day one launch in 2019. And if you wanted to learn a little bit more about Nervos just in a general sense, I'd recommend the Nervos Nation YouTube channel. They have some great videos out there that most of them are between 5 and 10 minutes, and they're little animated videos. They give a really great high-level overview about all this stuff. Okay, so why is the cell model important? Account abstraction enables smart contract-based accounts. So account abstraction, like I said, is a very important thing out there that's coming out today, because we are finding out very quickly that the rigid just private key, public key authorization of transactions doesn't work very well when you're trying to build smart contracts that really work. And not just for mass adoption, but for automation. Like, for example, like if you wanted to do a cross-chain action where you bounced one transaction through this chain, which connects to another chain, and it triggers something over there, that's not possible today because you would have to sign the transaction on this chain, and then you'd probably have to sign it on the second chain, sign it on the third chain. These things don't really work that well because of the methods that were imposed. So account abstraction is coming into a lot of chains. Most chains, I would say, that are in the top 100 are probably thinking about account abstraction or actively working on it right now, because it's basically saying that rigid model that was used for accounts is going out the window, and now we're going to actually just use a smart contract to control what a account is, what it can do and what it can't do. State rent is very important because, like I mentioned, it creates sustainable low fees, not artificially low fees like some other chains. There's actually been various ways that they have used the tokenomics of Nervos to very cleverly solve how do we keep fees low, but actually keep this environment sustainable for developers and users into the foreseeable future. Again, that's kind of a really big topic, but it's within our documentation about how that works. UTXOs enable scalability through parallel execution. I mentioned this one earlier. We need blockchains to scale a lot more than they can today if we ever want to really get to mass adoption. So that's something that's possible, UTXOs, and that's the cell model is based off of that. So we get massive parallel execution. First-class assets, which enables digital ownership and enhanced security. This is an interesting one. This one's kind of unique to Nervos. It's the user authority. The user, when they're holding an asset, they are at kind of like the top of the chain. Their authority trumps everything, including the authority of the smart contract. And what that means is that if the smart contract became compromised by a hacker, or the owner tried to do something shady and actually take away assets from the user, they can't actually do it. They can't do it without the user's permission. The user's authority always trumps everything else. And then flexibility is a cornerstone of the architecture. From the very beginning, the cell model has always tried to be the most flexible platform out there. And this includes times when it isn't easy or convenient to work with. And so ease of use comes with over time, with maturity of tooling and stuff. So it's something that is continuing to improve. But because they took this approach, they really set up a base that can stand the test of time. There's very little room to improve things. So you see some of the other ecosystems out there, they've now seen like that they're hitting these walls in certain directions. And this is because they've taken certain shortcuts or followed the path of a team that took a shortcut, and they didn't put into these levels of abstraction. The cell model really embraced this right from the beginning, and so it's a little bit again out of scope for today. But there's huge levels of flexibility that are actually available in the cell model, much more than you'll see in any other blockchain. A couple quick examples: transaction fees can be paid by anyone in any token. This is important just because, like, if you had a new user come into the ecosystem, normally they'd have to go acquire a token just to use your dApp. That's not always the case. The fees can actually be paid by anyone. You can, for example, think of it kind of like free shipping. If you had a dApp that genuinely shouldn't require a token, you can actually pay that fee for your users, and so they will still maintain the full authorization through their private keys, but you can actually pay that fee for them. So it makes the flow of what's possible much easier. CKB also used template-based smart contracts to reduce time and cost. What this means is that, for example, there are on Ethereum tens of thousands, possibly even more, maybe even hundreds of thousands of unique tokens that are now deployed. Every single one of those requires a separate smart contract. On Nervos, you could do the same thing with the single contract that is out there. All you have to do is supply new credentials to it. And basically any user can walk up and create their own token from it. And it's because it's using a template-based system rather than a deployment-based individual contract system. And this is an important thing because, again, reduces time and cost. This all makes things more sustainable. Smart contracts in any language that compiles to RISC-V. So this is an interesting one because as as we get more and more support for RISC-V, there are more languages out there that you're able to use. Any language that can compile to RISC-V can be used to, in theory at least, to create smart contracts because the RISC-V virtual machine that all smart contracts run on CKB, all it needs is that binary. If you can get to that binary, you can compile to that binary, you can use that language. Realistically, we would, of course, recommend that you stick to the languages that we actually have frameworks and libraries for. But in theory, like, we can support a lot more in the future. So if there is demand, if there are new languages that come out that are really, really great for specific things in the future, we can actually adopt those, and it won't require a hard fork or anything because we're just emulating a processor. So does this computer language compile into something that runs on a computer processor? The answer is probably going to be yes, so it will run on Nervos. An example of why this is important is any crypto primitives can be used without a hard fork. Now, I mentioned this a few times earlier before. This is important. This is a really important one because most of the other chains out there don't support all the encryptions that are available. And there's two main scenarios where this is really important. Number one, you're trying to do interoperability, and you're between two blockchains, but they don't support the same primitives. This is like they don't speak the same languages. So all of a sudden, you're faced with a really big hurdle that's very difficult to overcome. And a second scenario is looking into the future. All encryption over time eventually breaks, and this is because computers get faster and faster. We're on the verge of quantum computers now. They need to be upgraded. Sometimes vulnerabilities are found, so new encryption needs to be incorporated. And with Nervos, anybody can immediately adopt whatever encryption they need. All they have to do is supply a library. They don't actually have to wait for anybody. They don't have to wait for a hard fork to occur, which may or may never come. They can just go to work. Okay, so now we're getting into a little bit more of the technicals about how you're actually going to develop. And part of this is we need to teach you a little bit about the cell model. So first, what is a cell? A cell is the most basic structure for representing a single piece of data. So this is state data is what I'm talking about, data that's actually in the state and available for smart contracts to use. A cell is composed of 4 distinct fields: lock script, type script, capacity, and data. So I'm just going to quickly go through what each of these means. Number one, a script. A script is basically a smart contract. That's it. It's Nervos's version, which is similar to Bitcoin. Bitcoin also uses the terminology script. It's a very lightweight smart contract. Oftentimes you'll see that a true smart contract incorporates multiple scripts that are all kind of working together. So anyway, the lock script is designated for ownership. Every cell out there, every piece of state data needs to actually have an owner. You can assign that owner to nobody. You can put in a completely bogus address if you want to, but it needs to be assigned to somebody. The second one is TypeScript. Now, this is used to manage state transitions, which is a complicated way of saying that this is what a smart contract really is on Nervos. Most of the logic that typically goes into a smart contract, like for example, defining what a token is, all of that stuff typically goes into the TypeScript. And the third one is capacity. This is the CK bytes that are actually in the cell. Just like with Bitcoin has a field to indicate how many BTC is in a UTXO, capacity is Nervos's way of saying how many CK bytes are in the cell. Now, the reason we use the term capacity is because this is defining how much data can be stored in the cell. In Nervos, a CK byte, one CK byte equals 1 byte of data storage in the fourth field, which is data. So if you wanted to store a smart contract, for example, in the cell, let's say that a smart contract is 10,000 bytes, then you need to increase the capacity to be at least 10,000 bytes or a little bit more. And so you would do that by adding CK bytes to the cell. So it would take about approximately 10,000 CK bytes. Okay, so data. So data can be anything. You can store whatever data you want in there. You can store JPEGs, you could store JSON, you could store anything. It's not restricted, but typically what you want to put in there is smart contracts or valuable state information. Things like what is the token balance that you have. JPEGs, I wouldn't recommend it because that's going to be very expensive for data that is not that meaningful. But small pieces of data, such as token balances, and of course, smart contracts, that's an essential one. Those are really good uses of data that you can put into a cell. Okay, so what are scripts? So I already mentioned scripts are kind of like a smart contract. It's a small program that runs in CKB VM, which is our virtual machine. That's the RISC-V virtual machine. A script is actually a Linux binary, technically. It is if you actually had a Linux computer running RISC-V on a RISC-V processor, you could actually take that same binary and you could go and run it on a real Linux computer. Scripts are used to validate a transaction. As opposed to smart contracts, which are generation on, like for example, account model. I'll go into that a little bit more in a moment. The validation result from a script is always a yes or no answer. It's either yes, the transaction was valid, or no, was not valid. Here's an error code. It has 4 fields. So a script actually has, 3 fields. It has a code hash and a hash type. These are used to indicate what the code is that needs to be run, and arguments, which are provided to the script. This is arguments to basically the smart contract that tell it something about what it needs to do. Now, there's an important thing I just need to quickly mention is that we actually use the term script to mean 2 different things depending on context. Script could actually mean a data structure which is pointing to the smart contract itself, which is this. This is the 3 values. You'll see that in the actual code that we use. And sometimes we just say something like run the script. And we're actually talking about the script binary. That's the actual executable that runs in CKB VM. We use those interchangeably. Okay, so what is a transaction? On Nervos, a transaction describes a state transition. Transactions contain both start and end states. So this is a little bit different than on Ethereum, for example, where you submit a transaction and the transaction basically has like a function call which generates the next state, but you don't necessarily know what that state is. On Nervos, you see the start and end states. So it's validating these, not generating them. So transactions have 4 primary fields: input cells, output cells, cell depths, and witnesses. There are technically more fields than this, but we're not going to go into all of those. These are the important ones for a developer who wants to do something with the cell model immediately. Input cells are UTXOs, basically. That they represent the current state, and those are destroyed, and the output cells are created in their place, which is the future state. This is very similar to a Bitcoin transaction, which uses UTXOs. We have a second field, or a third field, I should say, which is the cell depths. This is data needed by the transaction. This is we'll show you how some of these works, but this is usually pointing to the smart contract that needs to execute, or something like Oracle data, for example. And then witnesses are arguments provided to the transaction itself. This is similar to Bitcoin. You can put in your signatures, right? If you're signing a transaction, that typically goes into the witness. But with Nervos, this is really like arguments being provided to the transaction itself. You can provide more data to whatever you need to in the transaction. It's not really limited. Just like with the data area, the witness area, you can kind of stick whatever you need to. It's anything that you need to provide to the transaction that is required for it to validate. And that also includes JPEG data. If you wanted to do something that is ordinal style, you can stick that into the witness field. Okay, so how does the cell model transaction compare to the account model? The account model is contract oriented. Cell model is transaction oriented. So the account model generates the next state. It's non-deterministic, meaning you don't know what that next state is necessarily, and you're charged fees even when the transactions fail. Cell model validates the next state. It doesn't generate it, it just validates it. It's deterministic. The transaction contains the previous state and the next state. So you can actually see this is what the state is going to be. It's guaranteed to be that, in fact. Either the transaction will confirm and it will be that next state, or that transaction will be rejected for whatever reason, and that new state will not be generated. There's zero guesswork involved. And it discards all failed transactions. So if your transaction doesn't go through, you're not charged a fee. And anybody who went through the previous bull market, I'm sure they probably got burned at some point by a transaction fee that was astronomical, $50 or more, trying to buy something, an NFT, for example, and it failed. They didn't get their NFT, but they were still charged that fee. Unfortunately, that's kind of the nature of the beast in the account model. But in the UTXO model, a failed transaction gets discarded. It doesn't actually get added to the chain. So this is a really quick example on what that means. So on a contract-oriented transaction, the state, let's say that it's currently 5. A transaction would say, call the increase function. And so it would actually execute this, and it would actually generate the next state, which would be 6. Now, in transaction-oriented, it's a little bit similar, but you can actually see that we start out with 5, and then in the transaction itself, there's old and new, and we specified to change it to 6. Then the transaction will run a validation where the smart contracts will actually execute, and they'll say, was the state transition valid? Could we go to 6 from 5? Like, for example, if this contract was saying you can only increase by a value of 1, then this would be valid. And maybe if it was 5 and then 10 over here, it would look at this and say, no, that's invalid. We're not going to allow that. So the start position and the end position are exactly the same, but it's 2 different ways of getting around it. One is generation, one is validation. Okay, what happens during transaction execution? We validate the structure of the transaction, number 1. This is just basic validation. Are all the fields in there? Are all the values within expected ranges? We verify that all input cells are live cells. It's like a UTXO. You can only use a UTXO which has not been consumed, or excuse me, the UTXO which has not been spent. That's the verbiage we use in Bitcoin. In the cell model, we use the verbiage live cell and dead cell. A UTXO, or a cell as we call it, can only be used exactly once in a transaction before it's converted from live to dead. And a dead cell can never be used again for any purpose. We check the input and output capacities, CK bytes. We're checking for basically in your transaction, did you try to create a bunch of CK bytes out of thin air? If not, your transaction is fine. So it will compare all those numbers across everything that's in the transaction. It will execute all scripts on every cell. So we'll cover a little bit about that in a moment, about how we actually assign scripts to cells. But these are basically the smart contract. We're just saying that every smart contract that executes must actually be valid. And then, so the script itself, when the scripts are executing, they are responsible for validating the structure of inputs and outputs. They validate the state data in the cell too, which is in our previous example going 5 to 6. This was showing some of that. Is the data that's actually being stored in the state and changing, is that valid? And they also are responsible for checking for the signatures that are in the witness field. So this is where we were talking about account abstraction. At the transaction validation level, the witness is not checked at all. It's actually the responsibility of the executing script to check the witnesses and figure out what's going on. That's different than the account model, different than Ethereum, where it is today, where it's actually a requirement for the transaction to do anything, regardless if the transaction is valid or not. It's the chain itself that is checking the signatures, not necessarily a smart contract. And then all scripts must be successful for the transaction to confirm. And this is kind of an important one, because this is what we had mentioned before about failed transactions in Ethereum still charging a fee. That's not the case on Nervos. Every script must be successful. If let's say there's 100 different scripts in a transaction, if even one of them fails, the entire transaction fails. So it's really the responsibility of the developer to make sure that their transactions are all valid, that they're submitting. And then, of course, it also needs to check for adequate fees. Fees on Nervos are very low, usually less than a penny, but they still have to be paid. Okay, so now let's take a look at what transactions actually look like. This is transaction sends 700 CKB from Charlie to Alice. So if you've seen a UTXO transaction in the past, you're going to probably recognize that this looks similar. This is a basic transaction where we are starting out where Charlie has a total of 1,000 CKB, which is contained in 2 cells, and he's transferring 700 to Alice. And then he's giving 300 back to himself, which is his change. This is his change cell. He didn't want to give 1,000 to her. He's only giving 700, and he's keeping 300 for himself. So these 2 cells on the left side represent the current state before this transaction executes, which is Alice doesn't have anything, at least not that's visible. Charlie has 1,000 in 2 cells. After this transaction executes, these 2 cells on the left, which are currently live cells, will become dead cells. And on the outputs, these new cells will be created after the transaction executes. And Alice will have 700, Charlie will have 300. This is a simplified example, by the way. Like there's of course more fields, there's fees involved and stuff. We've just taken all of that out just so we could actually show it. So this is a little bit more of a complicated example about showing what happens with the flow of live cells to dead cells. So we actually have 5 transaction here that we're looking at. And let's just say that all of these have successfully executed. You can actually see that we started all the way on the left with 1,000 CK bytes, and it moved through these different transactions into various places. Most of these cells that have been used in another transaction have now been converted into dead cells because they've been used. The red indicates that the cell is dead now. The green indicates that it's still a live cell. So you can see the flow of CK bytes through the system. We have 3 live cells at this point, 1 from the first transaction for 500, 1 from transaction for 4 for 100, and then 1 on transaction 5 for 400. This is a total of 1,000 CK bytes in the 3 live cells, which is the same as we started with at the very beginning with our first input cell of 1,000 CK bytes. Okay, so let's talk about the life cycle of a transaction. The first thing you want to do is you need to create a transaction skeleton. This is usually done with a framework such as Lumos. This is just an empty template that you populate with all of your information. You add your input cells. These are existing state that you need to be modified. You add your output cell. This shows the new state after confirmation. You add your change cells and transaction fees. And these are always based on the inputs and outputs. Usually you need to calculate this afterwards. And then you add your cell dependencies. These are script binaries and other needed resources. And so the most common thing that you're going to need is script binaries. Anytime that you execute a smart contract, like I mentioned the SUDT contract before, which is for tokens. If you use the SUDT token contract anywhere in your transaction, then you actually need to point you need to add that script binary to the cell dep so that the transaction knows, hey, this transaction is going to require this script to execute. Where is it? The cell dependency tells it where that is. And same that's for lock scripts as well. Any type of smart contract that needs to execute needs to be added as a cell dependency. You need to add any signatures. This is to prove ownership and authorization of input cells. This, because we have account abstraction, this depends on what you're doing. A lot of times you're going to be working with the default lock, which is our standard, most basic lock system that requires signatures. Sometimes if you're doing an automated system or something, because of account abstraction, you actually control what the validation is. Maybe it's not a signature. Maybe it's allowed to be run by anybody, just depending on conditions. These types of things are really powerful concepts, which are probably foreign if you're coming from like in the Ethereum world, but they really allow automation to occur and really allow us to push the boundaries of what you can do with smart contracts. Okay, so once you've created all of that, you go ahead and you broadcast your transaction to the network via CKB node, and then of course you just wait for it to confirm. The transaction has to confirm, or it didn't actually happen on the blockchain. You need to wait for it to confirm. And then we have a example in Lumos, which I'm going to click on just quickly so you can just take a very quick look at it. You'll probably see some of the things that are familiar. Transaction skeleton. We're adding capacity to the transaction, getting the sums of inputs, calculating change, adding, these are witness placeholders, but we'll populate those later. Here we sign the transaction. Very similar to what I just described is available in this source code that you can actually reference. And this is from the developer training course. There's a bunch of examples in there which you can actually just run the solutions. Like we have the solutions already provided on most of those. Most of those will just run right out of the box. I think actually they require a dev node. So you would have to set up a dev node, but we know what you guys are going to be short on time. If you're looking for example code that you can just run and then start to modify, this is some of the stuff you're going to be able to use. Okay, so script example. Let's look at SUDT. So this is the simple user-defined token. And so SUDT was the first basic token standard on CKB, similar to ERC20. It's about as simple as you can get in terms of a smart contract that actually has a real purpose. It's not just, for example, the number counter that I gave earlier. That's a contract that has no real purpose in real usage. But SUDT, this is the token standard that is active right now on Nervos's mainnet, and we use for DeFi and all that kind of stuff. It's actually very simple. So in the beginning, when the script executes, first it just checks, is the owner executing? It's checking. Basically, it's not technically checking the signatures, but it's doing the same purpose. It's checking, is the owner, is he the one who executed this transaction? If the owner of the token, the creator of the token, is that, immediately succeeds. It says, do whatever you want. We're okay with everything. If it's not the owner, then it actually does more validation. First, it determines the counts. And just like we had talked about with CK bytes, you can't create them out of thin air. Same with this contract for tokens. You have to provide tokens to be able to send them. They can't come out of thin air. You must actually account for this. And so it does this basic logic. Are the input tokens greater than or equal to the output tokens? We use greater than or equal to because if your output tokens are actually less than the input tokens, that's acceptable because you're actually just destroying tokens, you're burning them. But you can't create more output tokens than you provided in the input unless of course you're the owner. So if this passes, it'll go ahead and succeed. Otherwise, it'll go ahead and fail. Okay, so let's look at some of the logic. So this is just pseudocode about this logic. It's represented in code form. So we load up the arguments. The arguments to the cell are the ones that are actually telling you who actually owns this particular token, who created it. Then it checks the owner that it got from the arguments against the current user. If it is a current user, we just go ahead and succeed. Otherwise, we're going to go and gather we're going to count up the tokens from the inputs and outputs and compare them. And it looks like I had a typo there. I did a less than. It should have been a little bit different than that. But anyway, you get the idea. It's representing the same type of thing in this type of logic. So we can take a look at the SUDT implementation in Rust. And there's a little bit more to it, but it's really not that large of a contract, 93 lines total. And you can actually see that this code here matches the pseudocode almost exactly. It's a very similar system, very basic logic. This is something that you could probably go through in 10 or 15 minutes and have a general understanding about what everything in this file actually is doing. Okay, so now let's actually look at what an SUDT transaction looks like. So in this transaction, it's getting a little bit more complicated now that we're adding in some extra things, the cell depths and the witnesses, and our inputs are now representing more realistically what a transaction looks like with a token. So just like before, Charlie is starting with 1,000 CK bytes, but he also has 500 SUDT tokens. And these are, again, in two different cells. And so we're just adding those two balances together to get the actual total amount. Now the lock script, I couldn't fit that in because we had limited space, but that's a default lock we talked about. It's signature-based lock. So Charlie owns this cell and this cell. It requires a signature to unlock that. That is provided in the witness over here. And oops. The TypeScript for all of these, TypeScript defines the smart contract behavior. It defines the behavior of the cell. What is it actually representing? That's SUDT. And that's on all of these. So the one piece of information that is not actually reflected is that what is the data? What is the data of these cells? The data is a, let's see, I believe it is it's either 32 or I'm pretty sure it's no, let's see, a 64. It's like a 16 byte. It's a 16 byte value. I forget exactly. It's a numerical value in binary. Anyway, that's what important is, that the token balance is the data in this cell. You can hold, like I said, any type of data in this cell. When you're using the TypeScript for SUDT, that data is going to be the token balance. So that's the one piece of information that's not actually reflected here. So anyway, we're starting over here on the left side with Charlie. He's sending, again, Alice some tokens. And he's also sending her some CK bytes, by the way, because to create the cell, she actually needs some. Now, there's ways of getting around this, so you don't actually have to send CK bytes to another person when you're sending them a token. But to keep it simple, this is the easiest example to represent of what's actually going on. So we're just going to send CK bytes too. So if you add up all the numbers again, you're going to see 1,000 CK bytes, just like on the left side. On the right side, still 1,000. Then 500 SUDT tokens on the right side. And these all add up exactly like they should. And so this transaction would be successful when it's submitted. Now, since we used a lock script for Charlie, a lock script for Alice, and a SUDT type script. So these are the cell depths that are actually referenced, because anytime you use a smart contract, you actually have to tell it where is the binary that's going to use. So the SUDT binary was used for these tokens, and the default lock was used for both Charlie and Alice. It's the same lock script, so that was also included as a cell depth. Okay, so what tooling do I need? In short, we kind of recommend that you come and ask us on Discord, because there's depending on what you're doing, we'll be able to better direct you to what resources you need. But we'll go through a couple anyway. One of the first things that you're probably going to need access to, so you could submit basic transactions, is a CKB node. So we have a public node available that you can use for the testnet, and of course you can also set up a local devnet if you need to. We have instructions for both of those. Scripts and deployment. When you are writing a script, an on-chain script, my recommendation is to use Capsule with Rust. Capsule also supports C and I believe Lua at this point. There's a tutorial for Lua that just came out. I haven't actually even used it myself yet. My personal recommendation is still Rust, but it's up to you. It sounds like Lua might be a little bit more popular with some of the people who've used it recently. But Rust is going to probably be a little bit more mature. And depending on what you're doing, sometimes you have to go back to C because, for example, if you're using an encryption library or something that's only written in C, you can only find the source code for C. Sometimes you still have to use that. And Capsule will take both of those. So Capsule helps you compile and manage projects, so you can just compile them. And then you can actually deploy them through Capsule as well to the chain. There's also examples of this in the developer training course where there's some links to that throughout this document. So when you're designing your dApp front end and back end, typically that's going to be Lumos. So we actually just recommend that you go through some of the examples that are already functional out there so that you can kind of work your way through them. There's some in the layer 1 developer training course as well. And so the documentation on Lumos is unfortunately pretty spotty right now. I would say that the best way to make your way through that is to take an existing demo and try to rework it. If you're working with NFTs, I generally recommend that you look at Coda first. If you are working specifically with NFTs and nothing else, you can actually skip these first 3 tooling recommendations and go straight to Coda. They have a very large amount of documentation. They have public APIs, which are different. They're different from the CKB node APIs, and a whole bunch of examples that you can work with. So if you're doing NFTs, go to Coda first. They'll probably have everything you need. You might not have to actually touch any of the Lumos stuff or Capsule at all. And then if you're working with tokens, just basic fungible tokens, that's going to be, again, SUDT. You will probably, again, similar to the dApp front end and back end, you just kind of want to mess with some of the examples. Some of these have been linked in this slideshow here about that you could at least start with. With all of this stuff, feel free to join us on Discord. We will have people there for the entire duration of the hackathon to answer any questions, hopefully be able to point you in the right direction. Of course, once in a while, we do have to sleep as well. So there might be a couple periods where nobody's available, but please be patient. We will make sure that your question is answered as quickly as we can. Okay, and that's all I have for today. Thanks everybody for joining, and we look forward to seeing you on Discord. If there's any questions, let's see. Let me just make sure before I leave here. Let's see. Any questions? Matt, have you taken care of all the questions? Let's see. I'm not really seeing too much. So anyway, I'm going to go ahead and end it. I will be in Discord
we haven't had
with
anything
other developers in case anybody needs me. All right. Thanks. Good luck, everybody.